Alright, I'm going to skip over question number 1. I'll let you just look that up in your notes, but let's look at the second part here. The second one is we're asked to draw the normal lines. The first thing we're asked to do here is draw normal lines for each ray. Now a ray represents the path of a beam of light or any wave. So these are the rays, and what we want to do is draw normal lines for these. So let's go ahead and make this bigger. I think it'll help. So alright, let's try this now. I'm going to go ahead and draw normal lines here. I'm going to look here and say I think that this is normal there, and I think this is normal there. Now since it's that's the first thing I was asked to do. The next thing I'm asked to do is I'm asked to draw the reflected ray for each one. Well, I'm just going to do it one at a time. So now I'm going to draw the reflected ray for this one. So, angle of incidence is going to equal angle of reflection. Angle of incidence is going to equal angle of reflection. Let's go on to the next one. So here I've got this one here. Alright, let's make it a little bit bigger. We're going to draw our normal lines right here and right here. Not the best normal lines. It's kind of hard to work with this thing here. I'm just telling you, but here, I'm not complaining. So here comes my incident ray. So the outgoing ray, the angle of incidence equals the angle of reflection. It's going to look like that. And this one's going to come in this way. And it's going to go out at the same angle here. And you'll notice they came in parallel and they go out parallel. Let's try our next one. Here we have a concave reflector. So let's just go ahead and draw my normals. I think that looks kind of normal, and maybe that looks kind of normal. So now I have the incident ray is going to reflect at the same angle, and then this ray is coming in here and it's going to go out at that angle. Let's see how I did. No, that's not, no, I made a mess. This is not my best artwork ever, but let's just see how I did. Okay. Now, which of these three mirrors could be used to start a fire? Well, in order to start a fire, I've got to concentrate light. This is the one that concentrates light. The light gets concentrated right here at a point called the focus. This one spread the light out. This one kept parallel rays parallel. It is the convex ones that brought the light together that would allow that to happen. Now let's see what else we've got here. Let's see, yeah, okay, what type of mirror is shown? You know what, I'm not going to worry about this so much. I'm going to let you look at that one, maybe just on the homework help. Let's see, the number 10, let's try doing this one here. Draw the refracted ray. Okay, remember, to draw the refracted ray, you have to keep in mind that light is going to bend towards the normal when it slows down and away from the normal when it speeds up. So the first thing I got to do is I've got to draw normals, which means I want to make this a little bit larger. So I'm going to draw a normal line. Let's see, here's my normal line, more or less. Now what happens is I have the ray is coming in through the air. Now when it hits the water, it's going to slow down. So what I like to do is I like to say, okay, this is where it would have gone had it not been slowed down. But since it was slowed down, instead of going that path, I'm going to bend the path at the interface towards the normal. Not through the normal, but not this way on the other side. But instead of going this way, it's going to bend towards the normal. So I'm just going to go ahead and draw that line in like this. Alright, let's try the one next door here. We've got glass and air. So in this case, what I've got is, first I need to draw a normal line. There it is. And so what we find is as it comes into the air, it's going to slow down, and instead of continuing to go straight, it's going to bend towards the normal. So it'll get bent towards the normal. So it'll come in this way, slows down, and instead of going this way, it's going to bend towards the normal. Let's look at the next one. Now I'm giving you values of n. Remember, think of n, which is the index of refraction, as a multiplier of how many times slower than a vacuum. So in this material it travels 1.5 times slower than it does in a vacuum, and in this material it travels 1.8 times slower. So as it goes from this material, which is what is coming in at, into this one that it's traveling into, it's actually going to speed up. Instead of being 1.8 times slower, it's only going to be 1.5 times slower. So what's happening is it's speeding up. So what I do is I draw a normal line, and I say, okay, instead of going straight like this, since it's speeding up, it's going to bend away from the normal. So it's going to come in like this, and instead of following this path, that's a terrible line, it's going to bend away from the normal and go off that way. Awesome. Let's try some more. Alright. Complete the ray diagrams for each of these lenses. In this case, assume the light travels slower through the lens. Okay, so let me make this a little bit larger then. Alright, so I just got to draw these rays. This time they're not reflecting, they're refracting. So I'm going to go ahead and draw myself some normals. I'm going to draw a normal here. I draw a normal right here, which is coming in along the normal. I draw a normal right here. Now what happens then is, because it's going to bend, this one's going to come in, and it's going to slow down and bend towards the, oh that's terrible, towards the normal. This one's coming in along the normal, so it doesn't refract at all. This one's coming this way, and it's going to bend towards the normal. Now what we had to do is look at where they leave the glass at. Now they're going to speed up. So again, I had to draw normals here, and here, and here. And again, I apologize, it's hard to write with this stylus thingy. Now what happens is, instead of going straight, instead of going just straight this way or straight this way, they're going to bend away from the normal. So they're not going to approach it, they're going to bend away from it, which means this one's going to go this way, this one's going to go this way, and this one is going to be unrefracted, it's going to go through there. So this is basically what we're going to get. We're going to get a focus. Let's try this next one. Now the next one we have here is a concave lens. Again, I'm going to draw my normals. I'm going to draw them here. I guess I need to keep going. That was terrible. I'm going to try another one here and another one here. So what happens now, let me try redoing this one. This is terrible. Okay. In fact, I might even be able to erase. You know what? There we go. Let's try this one again. Sorry. Don't mean to be a perfectionist. Eric Sampson, perfectionist, hardly. Okay, so remember, it's going to slow down. So this ray is coming in, and instead of going straight, it's going to bend. It's slowing down, so it's going to bend towards the normal. So instead of going this way, instead of traveling straight this way, it's going to bend towards the normal. This one is coming in along, so it's not going to refract at all. This one, instead of going straight, is going to bend towards the normal. So what we find is, this one is going to come out that way. This one will continue straight on through. And this one is going to come in this way, and it's going to bend towards the normal. And we see what we have here is divergent rays here. They're spreading out, whereas the other ones came together. Now let's look at the next one. The next one we have is a biconvex lens system. And it's going to be a lot like the first one we drew. So what we have is, we're going to draw our normal lines. Oh, I'm going to try to do a good job this time. There's one, there's another one, and here is another one. So as the light comes in, it's going to, instead of going straight, instead of going this way, it's going to bend towards this normal line. So that means it's going to end up going this way. Now this one is coming in along the normal. Then when you come along the normal, you don't refract. In fact, as it goes out along the normal. So the ones that are normal, they don't refract. Now this other one, it comes in this way. And instead of going straight this way, it's going to bend towards the normal. So it's going to have to come up this way, just as this one's going to come down this way. So I think you can see what's going to happen is, well, let me just draw it. Here it goes. Now remember, we're entering the air now, so unfortunately we have to draw a new set of normals and say, okay, well, instead of going straight, it has to bend away from the normal as it speeds up. So this one is going to bend away from the normal. And similarly, the one down here, instead of going straight, it's speeding up, so it must bend away from the normal and go more at this angle. So it's going to go that way. And we see once again, we end up with a focus. Now let's keep going here. I'm going to try to do this in a single go. Alright, we have used the information. Hang on a second, I'm going to have to get a calculator to do this next part, aren't I? Okay, well, in order to do number 12, I have to use this information up here, and that's the index of refraction. Remember, when I say the index of refraction of diamond is 2.4, that means as light travels through diamond 2.4 times slower than it does through a vacuum, and when it goes through glass, it goes 1.66 times slower. And I'm sorry for the change in formatting that we got here. It's just part of my importing function, but here we go. So what I'm going to do here is, again, I'm going to draw a normal line. In both cases, I'm going to draw normal lines, and I simply have to refer to the information up above to see whether the light's speeding up or slowing down to decide whether or not the light bends towards or away from the normal. So in this first case, what I'm doing is I'm leaving benzene where the index of refraction is 1.5 and entering water where it's 1.33. So since water has a lower index of refraction, it means light only travels 1.33 times slower than it does through a vacuum, whereas with benzene it's 1.55. So basically, the smaller the number, the faster. So what that means then is, as it comes in this way, instead of going this way, it's speeding up, and when it speeds up, remember, it bends away from the normal. Now let's look at glass and diamond. If I look up here, what I find is diamond is 2.4, which is really slow, and glass is 1.6. So the light is slowing down considerably, and remember, when light slows down, it bends towards the normal. So instead of going this way, it's that terrible one, it's going to bend towards the normal because it's slowing down quite a bit. Now number 13 says, what is the speed of light in carbon tetrachloride? So carbon tetrachloride has an index of refraction of 1.46. If you'll recall, the index of refraction is basically the speed of light in a vacuum, which is represented by c, divided by the speed of light in that particular substance. So in this case, carbon tetrachloride is 1.46. I got that right up here. Is going to equal the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second, divided by the speed of light in carbon tetrachloride. Now what I'm going to do in this case is I'm just going to do the swap. When I want to solve for something in the denominator, what I do is I just simply swap it across. So I'm going to turn around and make this look like this. I'm going to say V equals 3 times 10 to the 8th divided by 1.46, and that, it turns out, equals, let's see, come on calculator, that equals, V in this case equals 2.05, we need more room, 2.05, oops, I can't get any more room. Darn it. Alright, I'll do it right down here. It's 2.05 times 10 to the 8th. So instead of 3 times 10 to the 8th, it's 2.05 times 10 to the 8th. Okay, so let's do number 15. What is Snell's law? Snell's law is, if I take the index of refraction of the incident material times the sine of the angle of incidence, it equals the index of refraction of the refractive substance times the sine of the angle of refraction. So now let's just apply that to number 16. So here I'm trying to find what is the index of refraction of the polystyrene. So I know that water has an index of refraction of 1.33 times the sine of the angle of incidence, which is 48, equals, let's just move this over a little bit, it's going to equal the index of refraction of the polystyrene times the sine of 41.5. So now all I had to do to find n is I had to divide this over here by the sine of 41.5, and what that's going to give me is an index of refraction of 1.49. So basically what I have to do is multiply 1.33 times the sine of this and then divide it by the sine of that, and that's going to give me 1.49. Now let's try the next one. Next one's a little bit trickier. Now I'm going to use Snell's law, but this time I'm trying to find what the angle is. Now since I'm trying to find the angle, I had to be a little bit tricky here. So let's just move this up and give ourselves a little bit more room to work with. Okay, so we're going to use Snell's law, and we're going to say, remember that the index of refraction of water is 1.33. So we're going to say 1.33 times the sine of 36 degrees. So in other words, the index of refraction of the incident material times the sine of the angle of incidence, which is between the normal and the incoming ray, is going to equal the index of refraction of the refractive substance, which in this case glass has an index of refraction of 1.66 times the sine of the angle of refraction. So what I need to do now is I'm going to go ahead and turn this into a number, and if I multiply 1.33 times the sine of 36, what I get is 0.78175, and that equals 1.66 sine of the index of refraction. Now I need to go ahead and undo what's being done to theta. So the first thing I'm going to do is undo multiply by 1.66. That means I'm going to divide both sides by 1.66. And what that's going to give me is 0.4709, which is what I get when I divide there, is going to equal sine theta of refraction. Now how do you undo taking the sine of something? Well, you simply take the inverse sine of it. So I'm going to look for that button on my calculator that says sine minus 1. It's the second function of the sine button usually. So I'm just going to go ahead and take the inverse sine of this. So I'm going to go ahead and take the inverse sine of both sides. Sine minus 1, sine minus 1. And if I take the inverse sine of this and the inverse sine of this, what I'm going to get is the the angle of refraction equals, and when I take the inverse sine of this, what I get is 28 degrees.